Welcome to the Organic Chemistry Podcast, or Dr. Brian Lloyd's Scribblecast. This is the Scribblecast, a podcast where you can download organic chemistry lectures for your personal study and enhancement. In this lecture, we're going to look at bonding models of the atom, and in order to do so, we're going to begin by considering waves. Waves, whether those of sound or light, consist of positive amplitudes and negative amplitudes. The positive amplitudes are those areas of the wave that rise above what is called the nodal line or the zero value line. Negative amplitudes are those that descend below. The regions or points which the wave crosses the zero axis are referred to as nodes. Nodes are those areas of the wave which have zero amplitude. Now, waves can be superimposed on each other. When you add two waves together, their waves or positive amplitudes can co-align. They can line up nicely, and so can the negative amplitudes. And when you have this type of combination, you get enhancement of the positive amplitudes, and the negative amplitudes get enhanced. And this is referred to as an in-phase combination. That is, the two waves add together in phase. If they are a sound wave, the sound gets louder. If they are a light wave, the light gets brighter. So when there's enhancement of the amplitude, intensity increases. And what would happen is you'd get a much larger wave moving through once they add it together. Waves, when they add together, can add out of phase. So if this is plus minus, on the bottom wave we have minus plus. Now, I've drawn this poorly, and I do apologize for this, but when the waves are out of phase, as in this case, when the waves are out of phase, what happens is that the amplitudes cancel out. And you end up with a wave function, if they're perfectly identical, of zero amplitude. So they interfere with each other and cancel each other out. Now, with this understanding of waves, we can go back in history and examine how this concept was originally applied to the electron. Now, in the year 1924, an individual named Broglie utilized two equations for energy to propose that electrons had wave character. Now, this type of concept is easily derived if you take Einstein's equation, energy equals mass times speed of light squared, E equals mc squared, and you combine it with the equation energy equals h nu. Now, nu is the Greek symbol nu. Okay? In high school, you probably use the symbol F for frequency. So the Greek letter nu is frequency. H is just Planck's constant. Now, I know that for light, c, the speed of light, equals frequency, the Greek letter nu, times lambda, which is wavelength. Lambda is wavelength. And so I can rearrange this and say nu equals c over lambda. And if I substitute that into this equation, I get energy equals hc over lambda. Now this is an equation that was derived and known for wave functions. E equals mc squared applied to particles. You can reach the conclusion de Broglie reached if you combine these two equations. Since they're both the energy, mc squared must equal Planck's constant times the speed of light over wavelength, lambda. So h is Planck's constant, c is the speed of light, lambda. Now, I can take this equation and multiply both sides by lambda, and if I do that, I don't change the equation because I'm doing the same thing to both sides. And you notice lambda divided by lambda equals 1, so that cancels. Then I can divide both sides of the equation by mc squared. If I do this, multiply by 1 over mc squared, the mc squared cancels the mc squared, and c cancels with the c squared. And I'm left with lambda equals Planck's constant over mass times speed of light. Now, massed objects cannot move the speed of light. This is impossible. If you have mass, you can never attain the speed of light. And so de Broglie modified this equation and said, okay, well, mass objects move with a certain velocity, and if a mass object is moving, since c is just speed of light, it's just velocity, let's rewrite this and say h over mv, where v is the velocity. And de Broglie said, what's interesting about this is this equation suggests that particles have wavelength. But since mass is on the bottom, large masses would have very tiny wavelengths, so small they're not observable. But if you get a particle that's small enough, say the size of an electron, who's much smaller than a proton even, perhaps it's small enough that the wavelength is significant enough that effects due to waves could be observed. And this was quite an astounding proposal at the time. Well, based on this proposal, a gentleman named Schrodinger he developed a wave function, a mathematical function that could describe the motion of the electron. A wave function for the motion of the electron. Now, from the equation for the wave function, if you square the wave function, you get the probability function, which leads to shapes, gives you the shapes of the orbitals. So Schrodinger's equation was quite a coup at the time. It allowed us to see these orbitals in which electrons find themselves, regions of space where there's a probability of finding the electron. But there was a problem. Schrodinger's wave function could only be solved exactly for a nucleus with one electron. How about it? Soon as you added a second electron, the very fact that you could never know where the electrons were introduced a variable for which there was no solution. And that was electron-electron repulsion. The strength of electron-electron propulsion could not be determined exactly because you never know where an electron is. Net result is an approximation had to be made. These approximations led to two theories for bonding. What were the two theories? Well, the first one we've already started to use, called valence bond theory. Valence bond theory you've already seen a bit of it in the drawing of Lewis structures. We use valence electrons to determine how we draw bonds, and the use of valence electrons is derived from valence bond theory. And we're going to have more to say about valence bond theory later. The second theory that is derived from Schrodinger's work and Schrodinger's approximations is molecular orbital theory. Molecular orbital theory. Now, these theories were derived from wave functions, which if squared give us probability functions. And remember, these probability functions gave us our s, p, d, and f orbitals. Now, in molecular orbital theory, we utilize LCAO theory. And LCAO theory simply stands for linear combination of atomic orbitals theory. LCAO theory simply states that atomic orbitals can overlap to generate molecular orbitals. Well, that sounds simple enough. Atomic orbitals can overlap. But let's pause for a second. We've already established that these orbitals are derived from wave functions. When we overlap them, what are we doing? We're adding waves. We're adding waves in the same fashion that we did in the opening of this lecture. So they can add in phase or out of phase. When the overlapping orbitals are in phase, what happens? Well, where they overlap, reinforcement occurs. And where they overlap is between the two nuclei. Now, if reinforcement occurs, that means that wave function is enriched between those two nuclei. And I'll show an example of this. Let's actually consider this. Let's take one electron. Okay, single electron orbital, hydrogen atom. And suppose the electron in here has a positive amplitude. And we're going to react it. And the orbitals are going to overlap. And the other electron in the other atom's orbital has the amplitude. And so these two come together and they actually overlap. What happens where they overlap? Well, what is this orbital? This orbital, this square of the wave function, is the probability of finding the electron. If you enhance that, what are you enhancing? You're enhancing the probability of finding an electron. What's that mean? Where there's overlap, there's a greater probability of finding an electron. So if there's a greater probability of finding an electron here where the overlap is, what happens over here? It decreases. If this probability goes up, the probability on this side must go down. So if there's an in-phase overlap, reinforcement occurs, and electron density between the two nuclei increases. Increases. And so what do you get? Well, when you're all done, you've got the two nuclei. And between the two nuclei, there is enriched overlap. The electron density between here is larger, but outside the nuclei, it's decreased. And I try to show that in my poor drawing. And the phase, again, is positive. Okay. Well, let's continue with this linear combination of atomic orbitals. Overlap two orbitals, but this time they overlap out of phase. Well, if they're out of phase, one hydrogen atom is coming in with a positive amplitude on its wave function, and the other hydrogen is approaching with its opposite amplitude wave function. And so when these two start to overlap, where they overlap, right, is out of phase. So the exact happens. Interference occurs. Electron density decreases. If the probability of the overlap region for finding electron drops, well, what happens over on the other side? Well, if it goes down here, if your chance of finding an electron is less here, it must have increased there. And so what happens when it all is said and done, you end up with something like that. So an out-of-phase combination leads to the electron density decreases. Between the two nuclei. All right. So what does that mean? In LCAO theory, an in-phase combination leads to electron density increasing between the two nuclei. If electron density increases between two nuclei, we have a bond. We get what is called a bonding molecular orbital. But when the two atoms approach each other and the atomic orbitals overlap out of phase, interference occurs. Between the two nuclei, electron density drops, and electron density moves to the outer edges. And that means between the two nuclei there's no bond, and this is referred to as a anti-bonding molecular orbital. Okay, let's consider hydrogen. A hydrogen is an atom with one electron, an element that has one electron. So two hydrogens can come together. And hydrogen has one electron in a 1s. Now, as these two hydrogens approach each other, so these two hydrogens are approaching each other, they can come together one of two ways. They can come together out of phase. Let's draw them overlapped. And when they're out of phase, one wave function has positive amplitudes where the other wave function has negative amplitudes. And this leads to a decrease of electron density between the two nuclei and an increase of electron density outside of the two nuclei. And this is our bonding orbital. So I'm going to asterisk this, our anti-bonding molecular orbital. That's what it looks like. When the two orbitals come together and overlap in phase, so this guy has a positive phase and this guy has a positive phase, and they're both coming together with amplitudes aligned, you get enhancement between the two nuclei. Between the two nuclei, you get an enhancement of bonding. Shrinks outside the nuclei. There's more electron density between the nuclei. And this is our bonding molecular orbital. Now what's interesting is if we go right back to remembering why atoms bond in the first place, it's to get to lower energy. Overlapping in phase produces a lower energy orbital. Overlapping out of phase produces a higher energy orbital. So these two atomic orbitals can combine and produce new orbitals. Now, what are we going to call these orbitals? Well, they looked at them and said, hey, these are spheres, and they're crashing together head on. So let's use the Greek letter sigma, that's the Greek letter sigma, and use it to mean head-on collision. Head-on collision. And so they said, okay, what had a head-on collision? Well, hydrogen uses the 1s, so we're going to call this a sigma 1s. And the one up above it gets called a sigma 1s. But because it's antibonding, we asterisk it, sigma 1s star. Give it an asterisk. Now, yes, these orbitals, one's high, one's low. There seems overall no gain, but the only orbitals you worry about are the ones with electrons in them. And if we add two electrons, we follow all of our rules we discussed earlier. The Aufbau principle, which says fill the lowest energy first. Pauli exclusion principle, which states no more than two electrons can occupy an orbital and must be of opposite spin. And Hund's rule, which says when you have equal energy orbitals, put one electron in at a time in each orbital of parallel spin. Well, we've only got two electrons, so they both end up in the sigma 1s for H2 gas. And since that's the occupied, you've gotten these two electrons in the free hydrogen atom to lower energy. And so that's a beneficial thing. Now, when we bring electrons or atoms together like this, we have to remember some basic rules. What are those rules? First off, no matter where or how you mix atomic orbitals, the number of atomic orbitals you start with must equal the number of molecular orbitals. In the case of hydrogen, I took one single atomic orbital, 1s, and combined it with another atomic orbital, 1s. That's 2 atomic orbitals. I got out 2 new molecular orbitals. What were they? They were the sigma 1s and sigma 1s star. The sigma meaning that these orbitals crashed head-on together. When we do more complicated orbital situations, like for atoms like carbon, nitrogen, which have 2s, 2p, we only mix orbitals of similar energy. Now this is an approximation and sometimes it's a bit erroneous, and we'll look at some of the results when this doesn't work out perfectly, but 1s combines with 1s because they're about the same energy. 2s combines with 2s because they're about the same energy. 2p's will combine with 2p's because they're about the same energy. All right. What is, let's change to red, this diagram that I made here called? Well, when we did electronic configuration, we drew atomic energy level diagrams. And in fact, the hydrogen, the individual hydrogen atoms are atomic energy level diagrams. But the thing you get in the middle is for a hydrogen or an H2 gas molecule. So this is called a molecular orbital energy level diagram, an MO energy diagram. Molecular, I'm going to run out of room, so I'm going to actually rub this out if I can. Make some room. And so we'll write down here molecular orbital energy level diagram. Molecular orbital energy level diagram. Now this molecular orbital energy level diagram has similar information in it as a valence bond diagram or a Lewis structure. Let's draw the Lewis structure for H2 gas. Here it is, nothing complicated. Or as I drew below here. This is the Lewis structure. This is a molecular orbital energy level diagram. If I look at the HH molecule in the Lewis structure, I notice I have a single bond. Well, I can determine the same thing from the middle section of our molecular orbital energy level diagram. I can define something called bond order. What is bond order? Well, bond order is a number that is determined by taking the sum of the bonding orbitals, the sum of all filled, that's important, filled bonding orbitals and I subtract minus the sum of all filled antibonding. I'm going to just write antibonding. Orbitals. So, it's sometimes given the symbol just B period O period. So, bond order is, I take all the filled bonding. Well, I see I have filled bonding here, one orbital that's filled, and subtract from it the filled antibonding. Well, there's no electrons in the antibonding, so it gets a 0. So bond order in this case is 1 minus 0, or equal to 1. So this is my bond order here. And the bond order in this case, is clearly 1. And bond order can tell you how many bonds. Do you have a double bond, triple bond, that type of thing. We also can look at the electron arrangement, and we see that these electrons are all paired up. Now, when the electrons are paired up, we've got some new terms to describe here. So let's clear this. If electrons are all paired up, your electron configuration is said to be diamagnetic. Diamagnetic is a term that applies when all electrons in your energy level diagram, your molecular orbital energy diagram, all electrons are paired up. So they're all paired up. You're said to be paramagnetic if you have one or more unpaired electrons. So you have a lone electron, one or more unpaired electrons. So in the case of hydrogen, we saw the electrons were paired up, so in that case it's diamagnetic. Now what I'd like to do is take a look at the case of oxygen. And what we're going to do here is try to apply our same approach we carried out for hydrogen. We're going to bring two oxygens together. And so we're going to start here with an oxygen that has a 1s. What's oxygen's atomic number? 2s and 3 2p's. And we're going to bring that together with another oxygen. 1s, 2s. And we've got 3 2p's. Now, we have already drawn what happens when 1s orbitals, which are spherical, approach each other. You can get in-phase and out-of-phase overlap. That is, the 1s combine as spheres. If you increase electron density between the nuclei, or if you decrease electron density between the nuclei. This is called the sigma 1s. This is called the sigma 1s star. We can do the same thing with the 2s because it's also spherical, if you remember the shapes. Of course, I didn't give myself enough room. And the lines, the hashed lines I'm showing are just showing how they connect. So you got the sigma 2s star here. And the sigma 2s. I can't draw them, running out of room. So I'll draw it to the side there. Okay. I'm going to actually raise these two p's a bit, if I can, just to make a little more room. Now we've got to talk about what happens to the two p's. Let's take a look at what the two p's look like. We've covered what shape the 2p orbital is. It's dumbbell shaped, but there's three of them. And so what happens is you have one figure 8 or dumbbell shape along the y-axis, one along the x-axis, and one coming out at you, which I tried drawing on a diagonal, and I'll draw it on the diagonal again. There. Now what happens if this approaches another oxygen's 2p's? Well, the other oxygen has the exact same shapes. One along the y-axis, one along the x-axis. And if I draw another one on the diagonal coming out at you, there you go. Now, it might be better if I try drawing one of these with different colors. So the one along the y-axis, I will use blue. The one along the x-axis, I'll use red. And the one coming out, I will use green. Now let's consider the collision. So here's the green one, that way. Here's the blue one. And here is the red one on the other atom. Let's ask about the collision. Remember, sigma meant head-on. Who is colliding head-on? Well, if we look at this, the 2p of this shape is colliding with this red 2p, and it's a head-on collision. So the red is a sigma collision. What about the blue and the green? How's the blue hitting the other blue orbital? Notice it's a side-to-side. It's not a head-on collision. When these guys are coming together, they're crashing together, the blues are hitting side-to-side. We need something, since it's not a head-on collision, to represent a side-to-side. And we're going to use a different Greek letter. We're going to use the Greek letter pi. This is the Greek letter pi. And it's going to mean a side-to-side. Side-to-side overlap, rather than a head-on collision between orbitals. And so both the blues and the greens are hitting each other side to side. So one orbital on one atom is hitting a red orbital on the other atom. So this orbital and this orbital are involved in head-on. Now it turns out head-on gives more overlap. Overlap means stronger bond. Bonding leads to lower energy. So the energy gap for the head-on collision is big when it's in phase. And remember, the out of phase component, the antibonding, must be the same amount higher energy. Okay. And this is a head-on, so it's sigma. this will be a sigma 2p. And this will be a sigma 2p star, because it's antibonding. Remember, antibonding is always higher energy. I'm going to fix that because that star, let's label this at the side. Usually you label them underneath, but I can make it much bigger if I put 2p star. Now, what about the other two orbitals on each atom? Well, those are the ones coming side to side. And because side-to-side overlap isn't as great, it doesn't come down as much as the sigma. But we get two orbitals. And then the ones that are antibonding don't go as much. And so this is a pi 2p. And you've got two of them. And over here we have the pi star 2p. And you've got two of those. And notice I had three 2p's combining with three 2p's. That's 6 orbitals. Notice what I've got. 1, 2, 3, 4, 5, 6. Let's take a closer look before we fill these electrons of what these orbitals look like. What happens when a 2p and a 2p collide together in phase and out of phase? Well, when the two 2p orbitals collide in phase and out of phase, in a head-on collision, it depends on the overlap of the lobes as to whether there's enhancement, whether they're in phase or out of phase. Now, when you look at an individual wave function for the 2p, it turns out the two lobes are opposite phase. So one's minus, one's plus. This minus plus is not charged. In fact, let's give it the amplitude. Represent wave function amplitudes. Let's give it a different color. So for it to combine, with the other one in phase, the lobes that crash together must have the same amplitudes. So two pluses must come together. What do you get when that happens? Well, I can draw my nucleus. And since there's enhancement of probability of finding the electron between the two nuclei, where they overlap, this gets increased. What about the lobes at the end? Well, if the probability in the positive amplitude spaces increases, that means the chance of finding it out where the minus signs are is less. So those lobes shrink. And so you end up with minus, minus, and those are amplitudes. A plus there. In other words, this is what that orbital, the sigma 2p, looks like. What happens if we combine these two out of phase? What happens when one 2p hits another 2p, and if this is plus, that one's minus? So when they come together, what happens when they're out of phase? Well, the region between the two nuclei leads to an interference pattern where the probability of finding the electron decreases. If the probability of finding the electron between the two nuclei decreases, it must increase outside. So where they overlap, there's a decrease. So the lobe on the outside increases. So if this was plus and that was minus, the lobes on the outside increase. And this is what the orbital for the sigma 2p star looks like. So notice we can figure out the shapes by how the waves combine. What about when we get side-to-side overlap? The pi 2p's and pi 2p stars, what do they look like? Well, we can do the same thing, except we want side-to-side overlap. What do we get? If these two are thrown together and their wave functions of their lobes, the amplitudes of their lobes, align and enhance one another. And so these come crashing together. What do we get? Well, where they overlap, there's enhancement. So above the two nuclei, there's going to be an orbital, something like that, because of overlap. And below the nuclei, there's going to be overlapped orbital. And this one's positive amplitude, that's negative amplitude. And so this is what the pi 2p looks like. An overlapped orbital like that. Likewise, if we continue, but these lobes are opposite each other now. They come crashing together. This one's a bit trickier to picture. Where they overlap, there's going to decrease. So if they overlap in this region, right here, then on this side of the lobe, the electron density drops. That means this side of the lobe is going to get enhanced, or the lobe's going to tilt away, if you like, from the two nuclei. So if I draw my two nuclei, what you're going to end up with will look a lot like a butterfly. And essentially what's happened here is in between, where the overlap occurred, they canceled each other out. So the lobes on the other half of the dumbbell were enhanced outwards. And this, of course, is our pi 2p star. So these are what these orbitals look like. We've already seen the sigma 1s and sigma 1s star for the hydrogen. The sigma 2s is the same as that. And so what we end up with, interestingly, are these strange and wonderful shapes for sigma 2p star, pi 2p, and pi 2p star. Right. Well, let's redraw our orbital pattern for oxygen. It's probably worth doing. It's a bit messy. See if I can improve it. Space it out a little better. And see what we can come up with. So right here, I'm going to have an oxygen. I'm going to put its 1s here. Quite a ways up, so I have more room. I'm going to put a 2s. And then all the way up here, I'm going to put 2p's. So right beside it, I have another set of 2p's for the other oxygen that's coming together, 2s. And I'm going to build myself 1s, the O2 molecule. Now the two 1s's come together in phase to produce the sigma 1s. Up here I get the sigma 2s star. The 2s comes down, I get an orbital. This is, whoa, that's sigma 1s. Sorry. So I've got sigma 1s, sigma 1s star, sigma 2s from the 2s orbital, sigma 2s star. So you notice when the two orbitals add together, you get a bonding and anti-bonding around each one. The two p's combine head-on, give you a pi 2p, a sigma 2p. Why sigma? Because it's a head-on collision. One of the orbitals combine from one atom with the other. These two orbitals come together head-on. Head-on overlap gives you a greater deflection in energy, so you get a big drop in energy, and then with the sigma 2p star, you get a big deflection. The pi's don't give you as much. We're supposed to make this better, and I think I'm making it worse. You have 4 2p's left. 2 on this oxygen, 2 on this. They give you side-to-side overlap. And with that, you get your pi 2p star and your pi 2p. All right. Let's use black for the electrons. How many electrons does oxygen have? What's the atomic number of oxygen? Oxygen has 8 electrons. In the oxygen atom, I put 8 electrons in. I follow the off-ball principle, so start at lowest energy first. Pauli exclusion principle says no more than 2 electrons in any orbital, and they must be of opposite spin. So there's 2, 3, 4. Hund's rule states that you must, when you hit equal energy orbitals, you must put 1 electron at a time in each orbital. 5, 6, 7, and then 8. Okay. Let's do this oxygen. 1, 2, 3, 4, 5, 6, 7, and 8. Now, when these two oxygens come together, they don't lose any electrons. You got one oxygen with 8, the other with 8. We have to put in 16 electrons in our middle section, which we have overlapped. What is the middle section? Well, the middle section is the O2 molecule, O2 gas. So we start with the off-ball principle again. Lowest energy. Pauli exclusion principle, no more than 2 electrons. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Follow Hund's rule. 11, 12. Start pairing up. 13, 14, 15, 16 electrons. This is the molecular orbital energy level diagram for O2 gas. Let's draw the Lewis structure for O2. O2 has 6 valence electrons for each oxygen. Total number of valence electrons is 12. Oxygen, 1, 2, 3, 4, 5, 6. Oxygen, 1, 2, 3, 4, 5, 6. Overlap till you get 8 electrons. And there you have it. There's the Lewis structure. Do they say the same thing? Well, let's do a bond order calculation, because the O2 in the Lewis structure has a double bond. What is the bond order in the molecular orbital energy level diagram description of O2? Well, bond order equals the total number of filled bonding levels. Well, what have we got? The sigma 1s is filled, the sigma 2s is filled, the sigma 2p and the 2 pi 2p's are filled. That's 1, 2, 3, 4, 5. We have 5 completely filled bonding orbitals. How many anti-bonding orbitals are filled? Well, the sigma 1s filled, the sigma 2s star is filled. But we've got a problem. The pi 2p stars are half filled. When that happens, you only count a half. So we've got 1, 2, 2.5, 3, minus 3. Bond order equals 2. So the bond order of 2 agrees with the double bond we see in the Lewis structure. So are these two descriptions, molecular orbital theory in the molecular orbital energy level diagram and valence bond theory in the Lewis structure, saying the same thing? Well, they do have one difference. Notice that all of the valence electrons in the Lewis structure are paired up, lone pairs or bonding pairs. 2 electrons in a bond, 2 electrons in a lone pair. But notice O2 in the molecular orbital energy electron has 2 unpaired electrons. Ooh, that's a problem. These two theories are not agreeing. Which one does experiment support? If we take a sample of oxygen, can we test it for unpaired electrons? We can measure the magnetic susceptibility of O2 and determine whether the magnetic field strength around the O2 molecule is that of a diamagnetic molecule or paramagnetic with 2 electrons. If we conduct that experiment, the measurement agrees with a paramagnetic O2 molecule with 2 unpaired electrons. That means the Lewis structure and valence bond description is wrong. But just because a theory is wrong doesn't mean it's not useful. The O2 description is much simpler. And as long as we remember there's 2 unpaired electrons, that is, O2 is a diradical, probably better drawn as having 2 dots, unpaired electrons. It's not an acceptable Lewis structure, but it is a better description of the experimentally observed O2 molecule. As long as we remember that, the valence bond description can be useful. All right, there's one more thing we have to look at in molecular orbital theory, and that is a perturbation that occurs when we don't use O2 or F2. What is that perturbation? And what I'm going to do for this is the N2 molecule right beside it. Now, what we've drawn here, the ranking we've drawn here in energy works for molecules like O2 and F2, the more electronegative ones. And in the case of the more electronegative ones, our assumption that 1s combines with 1s, 2s combines with 2s, and only the 2p's combine holds very well. But what happens when we have this pattern, okay, with 2 nitrogens? Now, 2 nitrogens will have the exact same thing happen. If I draw a nitrogen over here, I'll get the 1s, and then I'll have a 2s for nitrogen, and I'll have its 3 2p's. And the only difference is nitrogen's atomic number 7, so if I put in its electrons, it has 1 less electron. So the atomic orbital energy level diagram is 1 electron less for nitrogen. Now what's interesting is how these split out when I combine another nitrogen with it. And we'll put that over here. We get the exact same orbitals. The sigma 1s, sigma star 1s. The sigma 2s, the sigma 2s star. The sigma 2p, the sigma star 2p. The pi 2p, the pi star 2p. But there is a slight difference in the case of nitrogen, carbon, boron. What is that? Well, as I said, we get the sigma 1s here. And then we get the sigma 1s star. That's the same as what we got. Then we get the sigma 2s and the sigma 2s star. But then something happens. It's as if the pi 2p's all shifted downwards. We actually, before sigma 2p, get the 2 pi 2p's showing up. Then the sigma 2p, followed by the pi star 2p, and then up on top the sigma 2p. So it's as if these pi star and pi 2p all shifted down slightly, so the pi 2p shifted down past the sigma 2p. If we put in our electrons for nitrogen, how many electrons does nitrogen have altogether? Well, one nitrogen combines with 7, the other combines with 7, so N2 gas gets 14. 1, 2, 3, 4, 5, 6, 7, 8, Hund's rule, 9, 10, 11, 12. Pair them up, 13, 14. Okay, let's part these because it's getting a bit confusing. So here's N2 on the right. You notice the only difference is the pi 2p is below the sigma 2p. This type of pattern holds for nitrogen, carbon, boron, and beryllium, as well as lithium. But for fluorine and oxygen, we keep the normal pattern. Does the bond order work out for nitrogen? If you draw the Lewis structure for nitrogen, you're going to get something that looks like this. And you can try it. Do the Lewis structure for N2 gas. And you get that pattern. Suggests a triple bond between nitrogen. What does the bond order suggest? What does BO equal? Well, if I add up the filled bonding, I get sigma 1s, sigma 2s, pi 2p, sigma 2p, that's 5. Minus the only filled antibonding of the sigma 1s star and sigma 2s star, that's 5 minus 2, it equals 3. It's a triple bond. So the bond order agrees. In this case, the molecule's diamagnetic, and that agrees with the Lewis structure as well. I will give some handouts in class that will actually show this difference a little more neatly to you, and hopefully it will help. But that's pretty much it for molecular orbital theory in this section. To conclude, you'll notice that molecular orbital energy level diagrams are rather complicated, aren't they? And we only have 2 atoms in the molecule. What happens when we start putting in a lot of molecules, a lot of atoms to build a molecule? Well, what happens is we don't use molecular orbital theory unless you have some good computers. Typically, in this course, we will focus using valence bond theory, keeping in mind that valence bond theory can sometimes give you incorrect information, incorrect structural information, such as in the case of O2, where it suggested it was diamagnetic, but we showed that O2 was paramagnetic.